Good afternoon. We resume our reasoning on materials, and as we were saying last time, we were concentrating on mechanical testing, in particular on tensile testing, because they are the easiest one to perform. Of course, since a material is something to which a force can be applied and it's able to withstand that force up to a point, of course, after that damage occurs and then failure. Please bear in mind that we are talking on all these subjects because we would like to have an idea also for you on where is material research going. So basically, a main question about materials, as I was saying from the beginning, the main question is replacing materials with others which might be more appropriate for the use we want to perform, or which might be more performing, or which might solve some problems, degradation and so on. Therefore, there has been quite a considerable corpus of studies by Professor Michael Ashby from the University of Cambridge, which started this investigation in the 70s about the material selection, trying to have a, in a sense, a scientific material selection. What do I mean by that? I take material properties, I plot them. Of course, I need literature, I need papers, books, and so on to look at, take data from papers, books, reports, experimental reports, and plot them in a chart. The so-called Ashby's charts are characteristic for their structure with bubbles made with bubbles. And bubbles collect the data from one particular family or single material. And the question is that every bubble represents one thing which is important, and which is the fact that materials properties, and it's important from an experimental and an applicative point of view, have a kind of variations in properties. Here, for example, this is the main chart, which was the first which was developed, which is the chart of stiffness, Young's modulus on the y-axis, and on the x-axis you have the density, rho, which is expressed in kilograms per cube meters. What you can see is that the graph, as you can see, it's a logarithmic one, and you can easily see that 1000 is the density of water, 1000 kilograms per cube meter. So the density we usually call 1, defined with number 1. And you can see, for example, that polymers are grouped around that kind of density. And then you can have down there we have elastomers. Elastomers means rubbers. Elastomers are materials which are elastic to a point that they can proceed with very large deformation. They are able to deform to very large deformation returning sort of elastically, but without being brittle. Then we have foams. Foams are materials which are empty as a large part. They have empty volumes like honeycombs, and basically they are constituted by cells of different shapes, and they can easily be compressed. Foams usually. Some are rigid, more rigid, some are more flexible. Then at the center we have polymers, and we have natural materials. We have some natural materials are also shown, like leather. Please remember that in our course, as by the Ashby approach and also by the approach that is shown in your textbook, we consider engineered materials, synthetic materials, and natural materials as materials as a whole. We don't consider, we are not discriminating. We are not discriminating natural materials with respect to engineering materials. Also because we have used and we still use a number of natural materials. Think of the silica, for example, is a form of glass, but or clay, and etc. Then you have the composites. Composites, of course, you have glass fiber composite and carbon fiber composite, CFRP, metals, and mechanicals, which metals and ceramics, which can be non-technical or technical. Non-technical ceramics are the common ceramics, even concrete is then non-technical. Non-technical means that there is no procedure. We didn't apply any technology to reduce porosity. You know what is the problem also with pots, with clay bricks, for example. The problem is porosity, even with concrete. And if we don't apply any technology in order to reduce the porosity, one typical technology is sinterization, which means the application of pressure. Then they are non-technical ceramics. Otherwise, they are technical ceramics, like alumina. Even diamond can be considered technical ceramics because we didn't apply any technology to diamond, but diamond has a very low porosity. So non-technical means with high porosity, technical means with low porosity. Okay. So this is the main Ashby graph, which implies one important thing, that we are evaluating the relative stiffness. That means the stiffness with respect to density, with respect to weight. As a matter of fact, you can see that there is some relation between stiffness and density. You see that, well, that chart shows you a kind of sort of direct proportionality, sort of. So we can see that in very general terms, a material which is heavier, it's also stiffer, in very general terms. But we are interested to the exception. What does the interest of materials are materials which are not that heavy and stiff, which have a considerable interest. So if you compare, for example, steel and aluminum, this is a typical example. Steel and aluminum, steel has got a Young's modulus, which is higher than aluminum, which is about 3 times. But on the other side, steel weighs 3 times, has the density which is 3 times, about 3 times the one of aluminum. As the consequence, relative stiffness of steel and aluminum is about the same. Which has also another consequence, that the two alloys compete in a number of fields, because in some cases, well, steel is usually less expensive and it's more suited for larger thicknesses, but in a number of fields they are in competition. Okay, having said that, let's come back to what we were saying last time. We were talking about steel, and we were talking about steel as the material which is the alloy, I would say. As you may remember, steel is an alloy of iron and carbon of up to 2.06% of carbon. Usually there is much less than this, but there are other alloy elements. There are other elements which constitute the alloy, which you will gradually know. And use of steel, one of the first uses of steel, and one of the most successful uses of steel, which is still going on after hundreds of years, it's nailing. For example, on wood. Wood is a composite, and wood it's a kind of polymer matrix composite, in the sense that you have the matrix, the bulk of the material, which is a cell made in cellulose, which is a polysaccharide, and you have another polysaccharide which constitutes fibers, and this is lignin. The main difference between cellulose and lignin, I may have said already because it's important, is that they are both polysaccharides, but lignin absorbs less water than cellulose. Cellulose is not dissolved by water, but it absorbs water. Anyway, you may easily understand, even if you have experience with wood, that the resistance of wood, the tensile resistance of wood, it's maximum in the direction of the fibers. Okay, so we have nails of different shapes, round, head, headless, etc. Oval nails, and steel proved the best material for nails. In some cases, you may have steel which are plated with zinc or plated with copper to avoid in particularly corrosion. We are going to talk a bit about corrosion, which is an important problem in materials. But on the other side, as a bulk material, steel is very effective to produce nails. Different shapes of nails. The main question of nailing works because in hammering the nail on if you want to hang a picture, to hang your photograph on a wall, you nail with your hammer in the wall, or you can nail, for example, a piece of furniture, and for a wood beam, for example, you nail using a hammer. What happens in hammering a nail? In hammering a nail, you obviously apply a plastic deformation. We had said before that plastic deformation is not always a good thing, because in the long run it leads to failure. But in some cases, plastic deformation is essential for workability of the material. If you want to deform a material, for example, in turning wood, you want to deform it, having by some mechanical operations. Or if you want to nail something on wood, for example, you need to deform plastically. Okay, we call that work hardening. Work hardening means that in deforming plastically the steel, which constitutes the bulk of the nail, you also make it harder. So it's more difficult to penetrate, because this is hardness. But on the other side, it's easier, is more suitable to penetrate, for example, wood or walls and so on. This is important because we are able to follow also what happens to the sigma epsilon graph during hammering. So you imagine to start from the situation in A. There are particular types of steel which we use for making nails. Usually they are ferritic steel and they are not that ductile because in the end the nail needs to undergo quite considerable forces, so it cannot be that ductile. It should be quite hard. Should be quite hard for a start. Then you imagine that in hammering the nail into your structure, into your wall, into your wood, you pass from A to B to C to D to E. And let's imagine, well, of course, it's an assumption, but you could really do that. In practice, you could take a nail, apply some hammer hits, and then stopping, and then testing it, and then testing another one after a few more hammer hits, and so on. What happens? It's work hardening. It's defined as work hardening on the sigma epsilon curve, on the stress strain curve. What happens is that initially you have obviously an elastic point. At a certain point, you have the displacement, the removal from the elastic, the totally elastic behavior. So you have the elastic limit, which is also called the yield point. Yield point, which is synonym of elastic limit, but not all steel types and not still in all the situation has a clear yield point, because for example in D and E you don't find a clear yield point. What happens with yield point? With yield point you have the dislocations. You may remember that the dislocation are some defects of considerable extent which involve some non-negligible part of a grain. It's not just one atom of cation which is missing also. It's a real a row, for example, of cations which are displaced with respect to another one. And so the dislocation, it's I would say it's there as a defect, but it's steady, it's not moving. Then the dislocation are activated at the yield point, and they produce, as far as we carry on loading our material, they start activating. Of course, they activated not all the same at the same time. Please consider that in a metal there are a number, quite large number usually, of dislocations. And so they are not activated all this at the same time. And they start activating. As the consequence, the material has some load oscillations, which you see in particular in curve A. Then going on, what happens is that the final deformation of the curve, so the epsilon at which failure occurs, becomes lower and lower, and the yield point is less and less visible, in the sense that dislocations have been activated. Most of them have been activated already in B and C, so there is little more to do to activate defects, to activate their defect movement. So in practice, the activation of dislocation takes the form of two kind of movements. The movement of climb, there is a row of cations that tend to climb across the defect, over the defect, or the other one tends to glide on another one. So the one you can imagine that the row of cations climb over another row of cations, or another one which glides over it. So these are the two modes. Of course, as always, in most cases you have a mix match of two modes. But anyway, these are the two modes. Okay, so this is work hardening. Of course, you have at the end a slight increase of the stiffness, but in particular, you have that the material becomes harder and more brittle than before. In particular, you have a limited amount of plastic deformation left. Well, that there is a point that there are a number of types of nails depending on the surface. For example, in the house, if you have a main wall, you need to buy a larger head nail. If you have a small, just a small thickness wall, just one which is done, for example, using chalk cardboard mixture. In some cases, it's much easier for panels. Of course, the nail is going to be different. So the plastic deformation you need, so you need plastic deformation to hammer a nail, maybe more or less. And this influences also the shape of the nail. Okay. Of course, in all that process, since plastic deformation disappears, also necking disappears. You can imagine that necking is really very, very limited. Necking of your nail. You don't have any necking anymore. So you may have, if you test after work hardening your nail, you don't find until fracture occurs, you don't find really hardly any necking. So reduction of section. Okay, then we pass to toughness. As I was saying before, toughness, we were talking about I concluded last slide that we use concrete, which is not a very performing material because it's a material which is not very stiff. Even in compression, concrete is not particularly stiff, but it is tough. When I say tough, I mean that if you have a crack, that crack progresses with much more difficulty. So, in other words, it needs much more energy to progress. The more energy is needed for crack to progress, the tougher it's the material. Okay. Having said that, we start again from a stress-strain curve. Let's think it like a slowed extension curve without thinking of the initial length and of the section. Because we may imagine everything which is elastic and without any necking. In practice, you perform the toughness measurement. It's always the idea of the testing is always about the same. We have an extension and a load. And we try to establish the relationship between the two. Okay, the crack takes some energy to initiate, and it progresses reversibly. As you can imagine, until that point, which look at that point when the curve reaches its maximum, which we may imagine it's an elastic limit, and it is a sort of elastic limit, but it has another name. I would say that sort of elastic limit, it's the point where the crack hence progressing reversibly. Until that point, you could reverse the process and the crack wouldn't lead to failure of the material. Over that point, you have the crack propagation energy. So the crack progresses alone irreversibly. The whole of the area under the curve is the energy that you need to break a material by a crack. Then we have three ways in which we are interested to test the material. Of course, there is a tensile test of tensile test means that we have a crack and we tend the two extremes, the two ends of the crack in order for it to progress to failure. Mode 1, or we can have mode 2. So we have a crack and we allow one of the ends to slide with respect to the other. And then we have torsion. The torsion means that the two ends are torqued by an angle, one with respect to another, until breakage occurs. Okay. I'm showing to the left that these are examples of real cases. For example, mode 1, it's important when you want to divide a tree trunk, for example. You divide into part a tree trunk by hammering. And so by creating an indentation, a small crack that then progresses. At a certain point, it progresses alone. And you have, as you have experienced that, and then the tree trunk breaks on its own because the crack has arrived at a certain length, at a certain energy. It's a kind of activation energy at a certain point, it progresses alone. Okay, of course, this was the micro scale, but at the macro scale. But at the micro scale, what happens if you look at the crack? The crack starts to progressing irreversibly when a plastic zone is created at the crack tip. At the end of the crack, at the crack tip, a plastic zone is created, and then it progresses on its own. For example, we show here a crack tip in a steel for pipes. Okay, of course, this depends the propagation, the irreversible propagation of the crack depends on the material and on the crack length we are applying, length of the crack we have applied. And we have that formula K. K is the stress intensity factor. The stress intensity factor is exactly that kind of elastic limit, corresponds to that kind of elastic limit at which the material, after which the critical stress intensity factor corresponds to that elastic limit. The stress intensity factor is related to the stress and the length of the crack. And so units of K are megapascal per meter elevated to 1/2 because it's under the square root. A is under the square root. So A is the crack length. Okay, K can take whatever value, but we are interested to Kc. Kc is the critical value of the stress intensity factor after which the crack progresses irreversibly and therefore leads to failure, leads to brittle failure, I would say, in a very short time. Again, there is Kc for mode 1, mode 2, and mode 3. Usually we test in mode 1. Most used one is mode 1 because, as always, it's the easier of the three, the easiest of the three to perform. There are a number of test methods. In particular, there is compact testing specimen. You can see that you have the crack, which has a standardized length, and you need to pull apart the two ends. Or you have this kind of bending beam, the SEN specimen, the side edge notched beam. So you have this notch. Notch is less than a crack. Notch is really a little bit more than an indentation, has a small defect. You have this kind of span and you apply the force as in a bending test. This depends on the kind of material you want to investigate. In some cases, it is sufficient. You have the compact tension test. In other cases, you are more interested in this kind of flexural progression of the then you have the so-called Sharpie and ISO impact tests, which give you another information, not just toughness measurement, but it measures the fracture work of defective materials. You may easily imagine that in historical terms, Sharpie and ISO impact tests were developed before the compact tension and the SENB because they are simpler, much simpler, and in practice there is a pendulum which impacts a sample which might be which has a notch and might be disposed either side down or can be clamped side up. So you may have the notch down and the and without clamping the sample. Or in other cases, you may have the notch side up and the sample is clamped. In that case, you have the eyes. Okay, so basically you have a pendulum that impacts and gives you the impacts and gives you the information about the work of fracture. Work of fracture, depending on the section, of course. So it's a relative work of fracture. So you have kilojoules divided by square meters. Here you can have an idea of the toughness, and you can see that the toughness, for example, some categories of materials, this gives you only an idea of what can be the toughness of the different materials. In some cases, you may have large variation. For example, with polymer foams, you may have large variation because of it. Also because the stiffnesses can be very variable between different. Of course, as always, you can see that fracture surfaces give us the indications of how ductile or brittle is the fracture we observe. Again, we have an Ashby diagram. We have an Ashby diagram which gives us a number of indications. Here we have the yield strength. The yield strength is in practice the elastic limit. So the strength at which the dislocations start being activated, and the fracture toughness on the y-axis. You may see, for example, that concrete is down bottom left. Bottom left because concrete is a very, very low yield strength, but it has a decent fracture toughness. That's why we can say that we use it uniquely for its toughness, not for its yield strength, because it is very, very, very low. Also compared with glass, with polymers and so on. But in comparison with all this, it is tough. Because in fact, you can see the relative value, the lines of the diagram, you can see 0.001 millimeter, etc. These represent the relative value. so the relative the yield with respect to the so the fracture toughness with respect to the yield, fracture toughness with respect to the yield, and in fact you have some units which are basically length units, and therefore you can find out that concrete is not that bad. Concrete is quite high. It is on the line which is 10 millimeters, on the 10 millimeters line, and it's comparable with aluminum alloys, for example. Although, of course, aluminum alloy has a way higher stiffness and strength, but we use concrete for toughness. I'm talking about concrete because it gives you an idea of why Ashby diagrams are made, because they give you the impression of what we are using a material for. Of course, you need to have a book of Ashby diagrams. In fact, hundreds of Ashby diagrams were developed. I'll show some more of these during the course, although the course is quite short, so I'll try to do my best. Anyway, you see that metals are concentrated here. Again, the polymers are there, ceramics are technical ceramics, the ceramics with little porosity are there. What is very interesting is that there are some alloys based in particular on chromium, cobalt, and nickel that are really very capable of undergoing very high forces, and they have also a considerable toughness. So they are tougher than concrete, but on a stiffness which is few order of magnitude higher than concrete. These are, in particular, an example which I have chosen to give you an idea, since it's marked also here, are cryogenic steels. What happens with cryogenic steels? Cryogenic steels are steels which have been subjected to a treatment. So we have stainless steel. Stainless steel, it's a steel which is austenitic. Normally it's austenitic steel. Stainless means that it doesn't undergo corrosion, doesn't easily undergo corrosion because it includes chromium. Well, this is true to a point, but as a principle, when you introduce more than 18% of chromium, then you can be sure that the corrosion will be difficult. In fact, most of steel which is used, for example, in the kitchen, it's stainless austenitic. 18% of chromium, and of course, being austenitic, it has an amount of a gamma structured metal, which is nickel. You have always nickel in austenitic steel, but in the case of stainless austenitic steel, you have at least 18%, normally 18% of chromium. Okay, this is the general question about stainless steel. Then stainless steel is able to withstand corrosion, but or not developing corrosion, but is not able that much to withstand very low temperatures. In some cases, we need to undergo very low temperatures. For example, in application in pipelines, when you are going to extract oil, petrol in a very cold countries, like in the Arctic Sea and so on, you need the pipelines that go very down. And so you need cryogenic, they need to be treated in cryogenic tempering, a kind of heat treatment which is called tempering. In general terms, whatever heat treatment you do, not only on steel, on metals, different metals, but also on glass, it's called tempering. So you have a heat treatment at very low heat. So they started with liquid nitrogen, but then now it's possible to treat them even with temperature closer to liquefaction of hydrogen or even helium. So very close to the absolute zero. And in reality, what happens is that the lattice, the crystal lattice, is transformed from austenite into martensite. Martensite is a transformation of austenite. It's an elongation of the lattice of austenite. So you start from that cube and you get to a tetragon. So it's elongated and it's larger by volume, and it is a body, still body centered. It becomes body centered, so it expels a little bit. Remember that austenite is face centered, so it has 14 atoms into the lattice cell, and then here instead you are able to give more space, and you have a body-centered tetragonal which gives more space for carbon and for other atoms to move around. In practical terms, it allows you to have more plastic deformation, more at the crack tip, especially a complicated one, because what happens is that the 5 atoms which should be kind of expelled, the 5 cations passing from 14 to 9, in reality they move around in strange ways which might not be compatible with the shape of the crystal lattice. They have more space. In practice, what happens when you get to the crack tip is that the crack path, instead of being straight to failure, because what happens once you have exceeded K1C, the crack goes straight to failure. Instead, in this case, you may have some deviation and some tortuous paths, which means that failure is delayed. Failure is delayed means that material becomes more ductile. It was tough already, but it becomes also more ductile, and it's able to withstand also low temperatures. At low temperature, this is very useful because it delays fracture. Okay, so there is not just tensile tests. Of course, there is also the possibility that some deformation is obtained by shear tests. Shear test means that you have a deformation in the direction, the transverse direction, not only in tensile direction, but also in the transverse direction. You have a Young's modulus, which is the E modulus, is called with the letter E, and you may have another modulus, the shear modulus, which measures stiffness in the transverse direction, and it measures the slip between atom sheets in metal, hence the plastic shear deformation. In fact, you have the deformation which is in the direction, transverse direction. G is usually, in most cases, it's lower than E. I would say it's always lower than E because it's quite obvious that during tensile testing, you may have some shear deformation, but the shear modulus, the resistance to shear deformation is lower than the resistance to tensile deformation, which is expressed by stiffness. In practice, there is a relation which, as always, is your only value in ideal material, so in material which are homogeneous and isotropic and during elastic loading, which is about right for steel in the elastic part of its loading, as I was saying. you have this relation G is equal to E divided by 2 multiplied by 1 plus U. U is the negative of the ratio between transverse and longitudinal strain, and is called Poisson's ratio. In practice, Poisson's ratio, in most cases, takes values between 0 and 0.5. This is an example of how shear test is carried out. Therefore, we can give some more indications in typically on metals we have Poisson's ratio around 0.3. In rubbery materials, you may get to even to 0.5. What does it happen? What does it mean? That in reality, they elongate a lot. They resist to elongation, but they are even able to elongate a lot. But they resist very little to elongation on the shear direction. In practical terms, if you have a nu equal to 0.5, you have that G it's equal to 1/3 of E. 1/3 of E, which is the minimum physically value of that. And the consequence of this, the consequence of nu between being between 0 and 0.5 means that if you have an elongation, the material becomes in practice thinner, because it doesn't tend to it withstands much less the load in shear direction. So it's less stiff in the shear direction by 2 to 3 times, I would say, 2 to 3 times in general terms. There is an exception to that. There is an exception, which are the so-called auxetic materials. The so-called auxetic materials, which have been obtained from nature. They've been studied from nature because the scales, which are normally keratin scales, therefore obtained by a keratin scales, therefore obtained from keratin, from a protein, they tend to have some structure which is a concave polygon, as you can see by the magnification under the microscope. We usually always talk about convex polygons. Even when studying geometry at school, we always talk about convex polygons. So polygons which don't have any concavity. And even when we talk about foams in material science, foams are materials with voids, with cells which are designed in some cases, like in the sandwich panels, you have some honeycomb. Therefore, the cells are made in hexagonal form. They are made in hexagonal form, which implies one fact, that if they are a hexagon, they have all the same shape, and in practice, they tend to, their Poisson ratio is not far from 0, but they have normal behavior, so-called normal behavior, when we are able to stretch, when we pull them, they stretch. Auxetic materials, when we pull them, they tend to bend in different directions, giving an idea of inflation, of better sustaining or withstanding the load. And therefore, this is useful for salamanders and snakes, because in fact during their walking, when skates are pulled, they tend to inflate and to better sustain the weight. Since these materials have got also not very large body, they are able to better withstand the wear of the surface on which they walk, in a sense, or slide, to better withstand the landsliding or the sliding effect over the land. And this is useful for these animals, and as is useful also for our application, for engineering applications. In practical terms, what happens is that there were some shapes which were well known from the 90s for industrial production of the aesthetics. It is important that remember that the first idea of aesthetic material was given from the deviation from an honeycomb, from an hexagon. So you can see also the re-entrant aesthetics, for example, are constituted by hexagons, which have, instead of having all convex, having a convex shape, are concave. And so it's possible also to have other applications, other situations where the concavity is less evident but though present. For example, a combination of triangles and circle, like in the Kiro aesthetics, which always show when pulled, they show that inflation due to the having a Poisson's ratio below 0. In some cases, you can get as far as minus 0.5. And if we go back, minus 0.5 means that you can even have a G equal to E. In practice, you may have a material which has, when pulled, has the same stiffness on the direction of the length than on the direction of the width, which can present a number of interesting consequences. For example, for protection of our body, if you pull or if you push, then you have the same resistance on the other side, on the transverse side, which is the protection side. That's why, in practical terms, these oxetic materials, which were introduced here because these are examples of metamaterials. I will talk about metamaterials later on in the next lecture, because they have properties different from what we expect from materials. We expect that the pulled material would stretch. Instead, these are pulled material which inflate. And metamaterials means materials beyond the materials. In a sense, it means beyond the materials. It means that that effect doesn't depend on materials. You could ask, which kind of material could I make that? Well, salamander and snakes use keratin. In our case, we could use, for example, composites. We could even use paper. Paper would work very well for doing this kind of tricks. We could use foam because it's cellular already, so it's easy to work it out in that way, relatively easy. And in fact, a number of proposals have been done, for example, with rubber for shoes, which tended to sustain better the load of the body walking, the walking body, or this kind of helmet, which is a kind of dome, the so-called oxetic dome, which found also some application in architecture and so, which is protected. It's a foam down the helmet, which if an impact is received, so a compression, it tends not to encourage the compression. It doesn't get penetrated, but instead it tends to. Okay, and what else? Other possibilities have been studied about producing producing composite, oxetic composites. So composites, most composites which have been produced in engineering are fiber reinforced composites with carbon fibers, glass fibers, Kevlar fibers in particular, now also basalt fibers. And these composites um, can be made with two different fibers, with two different elongations. You may have some kind of plastic fibers which doesn't elongate much, and you can have a rubber fiber which elongates more. Kind of macroscopic structure, this kind of woven structure, you weave that structure and you are able to obtain that kind of oxetic deformation because there has been a lot of interest from the textile industries also in terms of jackets, safety jackets, which would withstand impact and tending to inflate instead of being strongly compressed. Okay, next time we will extend a bit these considerations about metamaterials, and then we will try to proceed across mechanical testing and try to see how other materials behave. Carrying on the evaluations on steel, but try to extend these considerations to other engineering and natural materials, of course, always keeping them together because when you start talking about polymers and about ceramics, nature has done much more and well before us has produced this kind of material. Okay, I'll put this recording once again on the YouTube and possibly also on the e-learning platform. The slides are going to be in a few minutes on my system, on my web page, which wasn't working this morning, but I hope it will do later on. Okay, and therefore see you on Friday at 11, as always. Okay, have a nice evening and see you next time.